Good morning all. Welcome to the class on functional analysis. Today we discuss a theorem. So before that we discuss a problem first. Problem is this: an infinite dimensional subspace of a normed space X may not be closed in X. For example, let X is equal to L infinity and Y equal to C naught naught. Then Y is a subspace of X, but Y is not closed in X. Since for to let the sequence xn equal to 1, 1 by 2, etc. 1 by n, 0, 0, etc. For let xn is equal to 1, 1 by 2, 1 by n, etc. That is, x1 is 1, 0, 0, etc. x2 is 1, 1 by 2, 0, etc. x3 is 1, 1 by 2, 1 by 3, 0, etc. etc. xn equal to 1, 1 by 2, 1 by 3, etc. 1 by n, 0, etc. So we have xn belongs to C naught naught for n equal to 1, 2, etc. And we have xn converges to 1, 1 by 2, 1 by 3, 1 by 4, etc. 1 by n plus 1, etc. And 1, 1 by 2, 1 by 3, etc. does not belongs to C naught naught. Therefore, C naught naught is not closed in L infinity. So we prove this theorem. This theorem states that let X be a normed space, then the following conditions are equivalent. 1. Every closed and bounded subset of X is compact. 2. Subset X belongs to X such that norm X less than or equal to 1 is compact. Third condition is that X is finite dimensional. So we are going to show that all these things are equivalent, for which first we prove 1 implies 2. So suppose that 1 holds every closed and bounded subset of X is compact. We consider the subset at A equal to set of all X in X such that norm of X less than or equal to 1. Then A is a closed and bounded subset of X. Therefore, by 1, A is compact. That is, set of all X belongs to X such that norm X less than or equal to 1 is compact. Now we prove 2 implies 3. So our assumption is 2. Suppose that set of all X in X such that norm X less than or equal to 1 is compact. If possible, let X be of infinite dimension. So let set 1, set 2, etc. be an infinite dimensional linearly independent subset of X. And consider set n is equal to span of set 1, set 2, etc. set n. Then set n is of finite dimension. Therefore, set n is a closed subspace of set n plus 1. Also, set n not equal to set n plus 1, since set 1, set 2, etc. set n plus 1 is linearly independent, and set n plus 1 does not belong to Zn. Therefore, by Ree's lemma, there exists an xn in Zn plus 1 such that norm of xn is 1 and distance between xn and Zn is greater than or equal to half. Here you are taking r to be 1 by 2. Now xn is a sequence in set of all xn such that norm of xn less than or equal to 1, and we have xn has no convergent subsequence. Since norm of xn minus xm greater than or equal to half for m not equal to n. So which is a contradiction to the fact that set of all xn such that norm xn less than or equal to 1 is compact. Therefore, the set xn such that norm of xn less than or equal to 1 cannot be compact. So we get a contradiction. So therefore x cannot be of infinite dimension. This proves 2 implies 3. Now we prove 3 implies 1. So our assumption is that x is finite dimensional. So we assume that x is finite dimensional. So suppose that x is finite dimensional, and let E be a closed and bounded subset of x. We prove that E is compact, for which we show that every sequence in E has a convergent subsequence. For which we show that every sequence in E has a subsequence which converges in E. So for which you consider a sequence xn in E. Let xn be a sequence in E, and you let y1, y2, etc. ym be a basis for x. Our assumption is that x is finite dimension. Suppose that dimension of x is m. So y1, y2, etc. ym may be treated as a basis for x. Now since E is a subspace, xn belongs to E that belongs to x. Since E is a subspace of x and xn belongs to E, implies xn is equal to some linear combination of y1, y2, etc. ym. So this is kn1 x1 plus kn2 x2 plus etc. plus knm xn. Now since xn belongs to E and E is closed and bounded, xn is bounded. Therefore by previous lemma, knj is bounded for j is equal to 1, 2, etc. m. Therefore by Bolzano-Weierstrass theorem, for k, we have k and j has a convergent subsequence. Therefore by Bolzano-Weierstrass theorem, for k and passing to subsequences several times, n1 less than n2 less than etc. such that the subsequence k, m, p, j of k and j converges in k as p tends to infinity for each j equal to 1, 2, etc. m. Therefore by previous lemma, the sequence xmp converges to some x in x. Now since xmp is a sequence in E and E is closed, x belongs to E. Therefore xmp converges in E. So this implies E is compact. Therefore, 1 follows. So we have assumed that E is closed and bounded. Now we have proved that E is compact. That is 3 implies 1. Now we have a remark. Let X belongs to X and R greater than 0. Then the closure of the open ball UXR is equal to set of all Y in X such that norm of X minus Y is less than R about X of radius R is the closed ball U of XR closure is equal to set of all Y in X such that norm of X minus Y less than or equal to R. So consider a ball and you consider a point X and this is your R. You consider a point Y here, Y on the boundary. So let Y belongs to X be such that norm of X minus Y equal to R. So it is a boundary point. We have Ty plus 1 minus T into X belongs to UXR for T belongs to open interval 0, 1. Remember that U is convex and Ty plus 1 minus T into X converges to Y if T tends to 1. So you have a sequence in UXR which converges to Y and Y is a boundary point. Therefore, UXR closure is set of all Y in X such that norm of X minus Y is less than or equal to R. So UXR closure is the closure of UXR. That's all for the day.